Okay, can we start now?
Yes.
Okay, today we are going to learn subspace. What is that? Okay, the definition for subspace is we have subset of the vector space. We have subset W here. The subset is subset of the of a vector space V. A subset W here called subspace of V if V itself a vector space under the addition and scalar multiplication defined on V. So this is the same operation on V. For the example, we know that, wait, where is another text? Oh. We know that we already talked about real number set is a vector space. And then, do you know rational number? Q.
Ada seorang ke?
We see. You're dead.
Yes.
Okay, we have Q here. Here is all of rational number here. And then we have complex number and integer. All of these are vector space with the operation addition and scalar multiplication standard or arithmetic addition and scalar multiplication. Okay, since we have the same operation here, and we knew that R is subset of, wait, see here. The set of ordinary numbers is a subset of the set of complex number. So we can say that R is a subspace of C, since we have R is a vector space and R is subset of C. Wait, let me complete it. And for another example, integer, also subset of R. So we can say Z, also subspace of R. Okay, this for the first definition. It means if we want to show that a subset of a vector space is a subspace, we have to show that the all axiom of vector space are satisfied. It means it's not efficient, right? So we have alternative way here. What is that? This theorem, we can use this theorem to show that the subset of a vector space is a subspace. We only show two axioms here. The first axiom we can call closed under addition, and the second closed under scalar multiplication. If you remember, the two axioms are part of axiom of vector space. This one, number one, I think the first axiom, and the second one is the sixth axiom. Okay, so we have W is a set of one or more vector from a vector space. It means W is a subset of vector space V here. Then W is a subspace of V if and only if these two conditions hold. Okay, this is our remark. The first condition we can call close under addition. And the second condition we can call close under scalar multiplication. So it means if you want to show the subset of vector space is subspace, we just show these two conditions only, not 10 anymore. Okay, for the example, we have subspace of polynomial degree n. Wait. Okay. Let n be a non-negative integer, and W consists of all function expressible in the form here. Where the coefficient here is R scalar or real number. Thus, W consists of all real polynomials of degree n, and this set is a subspace of vector space of all real value function. To show that this set satisfy both of the axiom of subspace, so we can write we show the two axiom. So if we have two polynomial here, P and Q, our P is here and our Q is this. Take a look at the form. We have general form is here. This is for general. It means if we have P and Q here, we can write another expression, but still in but still like this form. Wait, maybe we can use C0 plus C1x plus C2x squared plus C3 plus x cubed plus until Cn x to the power of n. So this is just the notation. So it means this is our general form. Okay, if we have P and Q, then we want to show that P plus Q is in W. Okay, for P plus QX, we have Px plus Qx. If we want to add two polynomial, A0 plus A1x until ANXN plus B0, sorry, 0 plus B1x plus until BNXN. So the product of our addition here, we just add each component, not component. What is that? So this one, A0 plus B0. And then this one, we have the coefficient of x, A1 plus B1x plus until En plus Bn xn. Okay, take a look at this form. Well, I can. Okay, take a look at this form. This also polynomial, right? Polynomial of degree n. Since we have this one, maybe you can say d0, d1x until the nxn. So this one is in W. And the second axiom, we want to show that the scalar multiplication k times p also in W. K times px, it means k times px here. We have, we multiply every element here by k. So we have k times a0, k times a1 x plus k an xn. This one also polynomials of degree n. So p plus k and k times p are in W. So W is a subspace of the vector space of our real value function. Okay, this one, the example of set that is not a subspace. Okay, we have W is the set of all points xy in R2. You can imagine coordinate Cartesian. But we have a property here. X, Y here is non-negative real numbers. It means this point are in the first quadrant. Okay, if you take a look, our W, our set is only in the first quadrant here because our X and our Y non-negative. Our set here is not subspace of two space R2. Why? Because this set is not closed under scalar multiplication. For example, we have point here, 1, 1. This is this U in W. But the negative -1 times U, we have -1, -1 is not in W anymore. I mean, it's not in the first quadrant. This is the third quadrant. So it means not close under scalar multiplication. So our set W is not a subspace of R2 here. So if you want to show, or if you want to determine whether our subset is a subspace, we have to be careful of our vector space here. Our vector space is R2. Okay, not that every non-zero vector space V has at least two subspace. V itself and the set that contain only zero vector here. Okay, this sum we can call zero subspace. Is there any question for this topic, subspace? I think this one is easier than to showing the vector space, because if we want to show the set is a vector space, we have to show the 10 axiom, but this time only 2 axiom. Okay, next, linear combination. What is that? A vector W is called linear combination of the vector V1, V2 until Vr if it can be expressed in the form here. K1 times V1, K2 times V2 plus until Kr, Vr, where Ki are scalars. For the example, we have vector u and vector v here. And we want to show that w here is a linear combination of u and v. How to show this? So we need to find two scalar. Okay, if you want to show w is a linear combination of u and v, so we want to find k1 times, we want to find two scalar k1 and k2. Such that w equals to k1 times u plus k2 times v. This means we have 1 minus 3, 0 equals to k1 times 3 minus 2 and 1 here plus k2 times 5 minus 1 and 2. Okay, from this equation, we have the equality of the component 3k1 minus 2k1 k1 plus 5k2 minus k2 2k2. From here, what we have here? Wait. Typo. Okay, from here, what we have? Oh, sudah benar. The second component we have K1, K2, and the third component K1 plus 2K2. Okay, from the last equation, the equality of the component, what we have here? We have system, linear system, how many equation and how many variable here? Hello?
Yes.
From the last
Yeah,
equation,
three equation.
three equation,
Yeah.
two variable.
Three
Okay.
equation
Huh?
and two
Two variable, yes. Okay. Be careful again. I warn you. I remind you. Don't use substitution and elimination. Use rule operation. You can use Gauss-Jordan elimination or Cramer's rules or the others method that we learned before. Okay, solving the system, we have, I already write to you. Okay, from the last equation we have 3a plus 5b equals to 1, minus 2a minus b equals to minus 3 here, the second component, and the component we have this equation. Solving the system using Gaussian elimination, we get a 2, b minus 1, and we conclude that w is equals to 2u minus v. Let's check our solution here. W equals to 2u minus v. 2 times u, so we have 6. 6 minus 5, we get 1 here. But the second component, 2 times minus 2 minus 4 plus minus 1, we get minus 3 here. And the last component, 2 times 1, we have 2 plus 2, minus v. 2 minus 2, we get 0. Okay, so we already showed that W is linear combination of U and V. What about our vector P here? So that our vector P here is not a linear combination of U and V. It means we don't have scalar such that W is equals to A times U plus B times V. But how to show that such a B scalar not exist? Okay, firstly, we show that P is a linear combination of U and V. It's mean we have to find scalar A and B such that P equals to AU plus BV. Okay, from the equality, we have this system. But if we solve this equation,
I found this on the web for solving this equation. Check it out.
okay, solving this equation, we conclude that the system is inconsistent. Why? You have to verify it. You remember why the system is inconsistent? If you construct the augmented metric, you have 3, 5, 8 minus 2 minus 0. Okay, let's verify. We have the first metric, the first row of the metric 3, 5, 8. Second, okay, what operation here? If you want to solve this system, we have 3 equation and 2 variable.
Change
What change rule?
-2 No, change negatives to 0.
Negative 2? What operation? You want to exchange the row?
3R2 plus 2R1.
Wait. R2?
No.
No. What? 3R2, you mean? So you want to change the second row?
I say 3R2
3R2?
plus 2
R1.
2R1. Yes. Change negative 2 into 0.
Okay. Let's check. The first row,
Am I right?
searching for the first row. And the second row, what we have? 0. And then the second column,
Yeah. Negative 3 plus
minus 3 plus 10. 7.
7. 7.
Wow, so big.
16.
And then this one.
1 to 5.
What?
1 to 5, right?
1?
1
Oh,
remains
okay.
same. 1 to 5.
Okay, sorry. I thought you guess what is our next operation here. Okay, next what operation?
3R3.
Hmm?
3R3 minus R1.
3R3 minus R1. So this one 0, right? 3R3 6. 3R3 minus R1. 6 minus 5. 1. This one.
3.
5, 7. Yeah.
Eh,
3R3 minus
0.
R1. Okay, next operation.
Five R1 minus 5R3 minus R1.
5R3. Okay, I think your operation is not right. I mean, if you want to change this one to 0 by R1, It means this one not 0 anymore. Okay, so if you want to change this one into 0,
Yeah.
you have to use the second row.
Yeah, yeah.
Okay, be careful. So what operation? R7R3 plus R2.
Minus R.
3.
7R3 plus, oh sorry, minus R2. And then from here we have the last row, our last row. We have 0, 0, and this one not 0, right? 49 minus, so we have 33 here. What does that mean? We have 0 times A plus 0 times B equals to 33. This contradiction, right? It means the system inconsistent. So no such scalar A and B exist. Since we have no scalar here, our vector P is not linear combination of U and V. Okay, I repeat. If you want to show a vector is a linear scalar combination, is a linear combination of two vector, it means we have to find two scalar here. If you want to show a vector is a linear combination of 5 vector, it means we have to find 5 scalar here. But if you want to show that a vector is not a linear combination of n scalar, maybe for general, it means we have no, or we cannot determine the scalar until we have this condition full. If you have the system is inconsistent, you can directly say that the scalar doesn't exist. Thus, our vector is not a linear combination of U and V. Is there up until here? No. Okay, the last one is spanning, but still related to linear combination. We have theorem here. If we have our vectors in vector space V, then the set W of all linear combination of our vectors is a subspace of V. It means if we collect all linear combination of our vector here, we get, or we say our set is W, then our W here is a subspace of V. And the second W is the small subspace of V that contain our vector that every other subspace of V that contain our vector must contain W. Okay, this is the definition for span. Span, we have set S here. Set contains our vector here. Our vector of vector space V. Then the subspace W of V consists of a linear combination of the vector in S. We call the space spanned by the R vectors. And we can say that the vectors, the R vector here, span W. If we write here, it's like this. We have, wait. MashaAllah. Why so hard to move? Okay, we have W here. The set of a linear combination are vector, right? So we have K1 V1 plus K2 V2 plus K3 until R V R. Okay, so our W here is same like this. Our W is all linear combination of vector V1, V2 until VR. And we can say this one spanned by V1 with V2, V3. For the example, wait. We have polynomial 1, x squared, x cubed, x until x to the power n, span the vector space polynomial of degree n. Why? Because its polynomial in Pn can be written as this. A0 times 1, A1 times x, A2 times x squared until an times xn. Which is linear combination of this polynomial. So we can write our Pn here spanned by 1x squared until xn. The next example, we have 4 factor here. We have factor 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0. These 4 factors span the vector space R4. Why? Because each vector V in R4 can be written as like this, linear combination of these 4 vectors. What if I remove one of these vectors? We have 3 vectors in R4. Are 3 vectors here span our vector space R4? What's your answer?
Yes,
Yes. Are you sure?
because in a vector they have 4.
We only have 3 vector here. It means, is this enough to span any vector in R4? It means, can 3 vector here span any vector A, B, C, D? Or let me X, Y, Z, U. K1, 1, 0, 0, plus K2, it's plus K3, wait, 0, 0, 1, 0, this, only this. Okay. Can we determine K1, K2, K3 such that we have X, Y, Z, and U here? Can we? We have 4 equation. Yeah. The first component we have K1 equals to X, K2 equals to Y, K3 equals to Z. What about U? Can we determine U?
0.
Oh, from where you say U is 0? we cannot conclude, right? So it means this 3 factor don't span R4. It's not enough to span the R4. Okay, next example. Determine whether U, oh, this one should be equals. We have 3 factor here. We will identify this 3 factor with the 3 factor span R3 or not. What your guess here?
Yes.
Yes, are you sure? If yes, it means we have to find a, okay, wait. It means for each factor B, I write X, Y, Z. Oh, ABC lah. In R3, and we express this vector into linear combination of the 3 factor here. K1U plus K2V plus K3V. Wow. If the answer yes, so it means U, V, and W span the R3. If not, so these factors don't span the R3. Again, we have this equation, and then we have a system. So you have to solve the system. Oh, wait. I cannot move. Okay. Okay, we have to determine whether any factor x in R3 can be expressed as a linear combination of the factor u, v, and w. From this equation, we have this. And then from here we have system, right? K1 plus K2 plus 2K3 equals to A. K1 plus K3 equals to B. And the last component, we have 2K1 plus K2 plus 3K3 equals to C. Okay, again, solving the system, we conclude that the system has no solution. Again, since the system is inconsistent. So no such scalar, K1, K2, K3 exists. It means U, V, and W do not span R3. If you take a look at this system, we want to find scalar K, right? But the equation still have many variables. It means the scalar also depend on the variable here, A, B, and C. For the example, for the previous, like the previous example, wait. Okay. From this example, what is our scalar here? Our scalar, the first scalar, K1, is A. The second scalar is B. The third scalar is C. And the fourth is D. All of the scalar depend on our factor here. If you construct this one, firstly we have A, B, C, D equals to K1 times 1, 0, 0, 0 plus until K4 from this equation, we have K1 equals to A, K2 equals to B, K3 equals to C, and K4 equals to D. So just express our any vector in our vector space as a linear combination of this vector. Like the first example, we have our scalar is A0, A1, A2 until AN. This one our scalar because we have this one our vector. These vectors span our polynomial. Okay, is there any question? I have Simon for you. For number 1, so you only show are the two axioms of the subspace satisfy the first set. Our S here is subset of R3, but the component only A11 here. So our set S here, A is any real number, but the second and the third, the component should be 1. Do you get it? The form of this S is like, you can say 1/2, 1, 1, still in S. And then 3, 1, 1 also in S. What if I have factor 3 minus 2, 0? Is the factor is in S? If we have 3 minus 2, 0. Okay. What is the answer? Hello?
No.
No, okay. For B, our set is 2 by 2 matrices. But for subset S, our vector space 2 by 2 matrix, and our S here 2 by 2 matrices, but only for determinant of the matrix is 0. For C, our vector space polynomial of degree 2. Our set S here, polynomial of degree 2, where sum of the coefficient is 0. For the example, I have polynomial with maybe 1 plus x minus 2x squared. This is polynomial in S. Why? Because we add a0 is 1 plus 1 minus t minus 2 equals to 0 here. So this polynomial is in S. For all three, you determine subspace or not. Is this S subspace of R3? Is this S subspace of 2 by 2 matrices? If this set subspace of polynomial of degree 2. Number 2, express this vector as linear combination of 3 vectors. You have to find the 3 scalar here. So this one equals to k1 times u plus k2 times v plus k3 times w. You have to find k1, k2, and k3. Number 3, similar to number 2, you have to find 3 scalar. Number 4, determine whether these 3 vectors span R3. So it means if you have any vector in R3, is the vector can be expressed as a linear combination of V1, V2, and V3. Is there any question regarding this assignment? If you have any question, you can ask me on WhatsApp. Okay, if no question, I think we can stop our session today. Thank you very much for your attention. Good afternoon.